All right, guys, we're going to take a look now at section 8.2, part 1, okay? And then I think I'm even going to break it down into A and B. It just loads so much easier on YouTube. I know it's a little bit more annoying, but let's see how we do. But I think we're going to have to break part 1 into 2 pieces as well, okay? All right, so now we're changing gears. Now every other lesson is series, okay? And we're just going to keep building rules or different things that we're going to use. So eventually I'll give you a sheet of everything that we've covered. I'll maybe even do it sooner than later. But okay, so let's compare sequence to series. A sequence is just a list of numbers. Notice they're separated by a comma. Okay, 2, 4, 6, 8, da 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 da. A series is now when you add the numbers together. We want to do 2 plus 4 plus 6 plus 8. This is sigma notation, right? This is sigma notation. This is a way to show that we want to add. This is the rule to make these, right? When n is 1, it gives us 2. When n is 2, it gives us 4. When n is 3, it gives us 6. But then this guy says, hey, now we don't want to just make the list. We want to add them together, okay? And if we have to, anytime you can pull a number out, that's okay. So if it's a constant, you can actually just add these up and then take that answer times 2. Okay, now usually you go from 1 to like 7, 1 to 8, but we're going 1 to infinity. Okay, now this is where it gets a little crazy. This list, when I add it together, so here's 2, here, and that answer is 2, right? That makes sense. Now if I do 2 plus 4, I get 6. If I do 2 plus 4 plus 6, if I do 2 plus 4 plus 6, I get 12. If I do 2 plus 4 plus 6 plus 8, I get 20. So this is called a partial sum. As I add each together, now I can actually make a sequence of the answers to the addition. This, it's called a sequence, because notice I'm back to commas, of partial sums. But this is the answer if I add 1 together, if I add 2 together, 3 together, 4 together. So there's a kind of a couple things going on here. So we'll try to address which one we're looking at. Okay. All right. Now, some things that we need to realize for series. Make sure you can see this. Okay. Actually, let me pause. If you want to pause and write some more stuff down, I try to have it go a little bit quicker, but if you want to pause right now and write that down, you can. Okay. Same with this. If you want to, after we're done, then I can pause for a second, or you can pause and then write it down. There's special series. Harmonic series is very important. Okay. The harmonic series, if you have 1 over n, okay, and you're going from 1 to infinity, the harmonic series always diverges. Okay, the harmonic series always diverges. Now notice we're talking about the harmonic series, okay? If you, let me do this real quick. If you have like 1 over 1, okay, comma, 1 over 2, 1 over 3, 1 over 4, right? Can you see? I'm just going to show you this. With a comma, that's a whole different story. If I'm talking about a sequence, that's different. But as soon as I talk about adding them, that's going to diverge, which is a little weird. We're used to this. We now got to change our gears that we're going to be adding. We put plus dot dot dot. So as soon as we talk about adding, as soon as we talk about a series, it diverges. Okay, so keep that in mind. Really, there's a huge difference between sequences and series. Okay, sometimes I wish we didn't even start with sequence. It's kind of a good introduction, it really is, but the rest of the time we're talking about adding, so that's going to change some things. So this one, if you add them, it's always going to diverge, and it's called the harmonic series. Okay, the other thing is the geometric series. The geometric series is a times, and a is just a number, a is a number, r to the n minus 1. Now this is where this lesson is going to get a little dicey. If it's n minus 1, we have to start at 1. There are some cases where we start at 0. It doesn't, because we're adding so many things together, it doesn't really matter if we're starting at 0 or 1. It doesn't matter if we call the first term 0 or 1. It just doesn't matter. So if we're going to say that, hey, we're starting at 0, then this just has to be r to the n. Okay, so this is going to come back and get us just a little bit, so we'll try to reference this. But the good thing is, if the absolute value of r is less than 1, it converges. And if it's greater than or equal to 1, it diverges. Okay, this is the geometric series. You have a number, and you're taking it r to the n, or r to the n minus 1. Okay, and if it converges, so if it converges to a divided by 1 minus r. Okay, so the geometric series is one of the very few series where we can figure out what it converges to. So if it converges to a minus r. Okay, so if you want to pause, if you didn't get that written down, go ahead and pause it and write that down. Okay, there's one more thing. Actually, two more things. All right, so the test for divergence. Okay, if you have a sum and you have a rule, if you go and just do the limit on the rule, which is we're kind of like changing it from a series to a sequence. Okay, so this is actually a big difference here. We're actually just going to take the limit on just the rule. So we're going to look at it as a sequence. Okay, if that does not equal 0, so any number besides 0 or doesn't even exist at all, then it diverges. Then the actual series diverges. So we look at it as a sequence. And we're going to have this most of the time. If it doesn't equal 0, then the actual series diverges. Okay, so this, we're actually looking at it as a sequence. Okay, but we're going to actually be able to state it. We're actually going to be able to state the series diverges. Okay, this is important. If it equals 0, it's not like we can say if it equals 0, then it converges. If it equals 0, we're back to the beginning. We have no idea if it diverges or converges. If it doesn't equal 0, it diverges. If it does equal 0, it still could diverge. It still could converge. Okay? We can't say if it equals 0, it automatically converges. We have no idea. Okay? So that's pretty important. Okay, and then same thing here. If you're adding things, it's okay to look at each one separately. That is more than fine. See how I'm adding two things? It's okay to look at things separately. Okay. So that is that's kind of like our notes. We're going to reference those. I know we're still getting used to them. So I'll kind of keep those over here. All right. So the directions determine whether the series is convergent or divergent. If it is convergent, find its sum. Okay. So even if we add from 1 to infinity, is it actually going to add to a specific number? Now let's face it, most of the time the answer is no. Okay, so, but we're going to try to come up with some times where we can actually find the sum from 1 to infinity. That's kind of crazy. All right, so our first example, 1 to infinity, we're doing -3 to the n minus 1 and 4 to the n. Okay, so now this is where right away it gets a little crazy. Let's see, where's this? Where is that guy? Geometric. Okay. If it's 1, it has to be n minus 1. Okay, if it's 0, then it has to be n. So we have both here. That's a little bit of a problem. This I cannot change. So if it's 1, I need it to say n minus 1. So this is beautiful. This guy, we need to do a little bit of work. Okay, this, we're going to rewrite it. See, let's write it and then we'll talk about it. We're going to rewrite this as 1/4. Well, yeah, that's fine. Times, we're going to do -3 to the n minus 1 and then 4 to to the n minus 1. Okay, so now where is that coming from? Well, let's say n is 3. So if I plug in a 3 here, I have 4 times 4 times 4. Okay, I needed to say n minus 1. So now if I plug in a 3, I'm really only going to have 2 4s here, right? Because 3 minus 1 is 2, but I need it to say 3. I can't change the problem, so here is my third 4. Okay, let's say if I do n to the 7th, or I'm sorry, if I make n 7, I have 4 to the 7th, 4 to the 7th. So I need 7 4s. If I plug it in here, because I really needed to say n minus 1, if I plug it in here, if I plug the 7 in here, I really only have 4 to the 6th. Here's my 7th one. So if you need an n minus 1, you just have to write an extra base over here. Okay. This will give me, if I want 4 to the 7th, this will now give me 6, and here's my 7th one. If I want n to the 10th, that's what I want. I have to have 4 to the 10th. I have to have 4 to the 10th. So now when I plug in 10, I only get 9, but here's my 10th one. Okay, and that's big because now I can rewrite it like this. I'm going to rewrite this as 1/4, and then because these exponents are the same, I'm going to rewrite it as -3/4 n minus 1. Okay, and this is now geometric. This is geometric. This is a to the r n minus 1. Go back, look in your notes. Geometric, 1 to infinity, it has to say a to the r n minus 1. Okay. So that means my r is -3/4. Okay. What's the rule? If the absolute value of r is less than 1, it converges. So is my r, the absolute value of r, is that less than 1? Absolutely, so it converges. Okay, and what does it converge to? A over 1 minus r. Okay. So determine whether the series is convergent or divergent. We did that, converges. If it is convergent, find its sum. What is all of this going to add up to? Even if I'm going to infinity, it's going to add up to a, which is 1/4, over 1 minus r. Now just be careful, r is -3/4. Okay, so now I just got to figure that out. This is 1/4. This would be what, 7/4? You grab a calculator if you want. Can you guys see this? Barely. 1/4 times 4/7 instead of dividing, multiplied by the reciprocal, that cancels, and so it adds up. That is crazy. It adds up to 1/7. Okay, so it converges. The sum, now we're talking about the sum, adding all of these up, plug in a 1, plug in a 2, plug in a 3, and add them together is going to add to be 1/7. We're talking about the sum. Okay, that's kind of crazy. Okay, let's try another one. Let me put that one over there. Okay, let's see. Let's try this one. How are we doing on time? Okay, let's do a few more. Summation n equals 1 to infinity, 6 to the n over -5 to the n minus 1. Okay. Okay, so we're starting at 1, which means if we think it's geometric, and when your variable is an exponent, you're thinking geometric. When your variable is an exponent, you're thinking geometric. We need it to be n minus 1. So this one is, this time this is beautiful. This we need to change. Okay, so we're going to change this, n equals 1. We're going to rewrite this as 6 times 6 to the n minus 1. Okay, and then we've got -5 to the n minus 1. Okay, let's say n is 4. I need to have 6 to the 4th. I can't change the problem. So I need to have 6 to the 4th. When I plug a 4 in here, I only have 6 to the 3rd. There's my 4th one. And that's okay. I just wrote it a little bit differently. These two are still saying the exact same thing. If my n is an 8, I have to have 6 to the 8th in order to keep the same problem. When I plug in an 8 here, I only get 7, but there's my 8th one. Okay. All right, so now written like this, we're in good shape. 6, and then I'm going to do 6 over negative 5 to the n minus 1. And now that officially is geometric. This is my a, and this is my r to the n minus 1. Okay. All right, so my r is negative 6/5. What about the absolute value of that? If it is greater than or equal to 1, it automatically diverges. Okay. If it's greater than or equal to 1, then it automatically diverges. Beautiful. So it's geometric. I'm going to have you eventually on your test like write what it is. So, and here, like if you put this, okay, but I want you to somewhere state that it was geometric. Even if you just write geo, and you don't have to even write the whole thing, but somewhere along the line you're going to have to tell me, because we're going to have a lot of these, and so you're going to have to tell me what you used. Hey, I know this was geometric, and then show that it diverges. Okay, let's try another one. Let's do summation of, now this is 0. We're going to start at 0. Okay, and then this is going to be 2 pi to the n, and then it's going to be 6 to the n plus 1. Okay, turn that so you can see it. Okay, so this time we're starting at 0. If we start at 0, where's my thing here? If we start at 0, we're just looking for r to the n. Okay, so this is, the top is beautiful. This one we can almost kind of see, right? It's kind of nice when it's this way because I can just split that up, right? If I have, we did this in the last section, 0 to infinity, this is 2 pi n. I can even write this as 6 to the first times, oh geez, this should be n. Sorry, that should be n. I'm just taking it right from there. 6 to the n. So if I'm adding, I can split it up as multiplication. So that's beautiful. Okay, so now let's rewrite this. I'm going to do 1/6, and then I'm going to do 2 pi over 6, and they both have, once I fix that one, they both have an exponent of n. What do we have, guys? This is geometric. This is geometric. Oops, that's not good. This is a, and this is r to the n, and I only need an n because I'm starting at 0. Okay. So what's the rule for geometric? Look at your r value. R is 2 pi over 6. All right. Now, what is 2 pi? 2 pi is what? 6.28. We'll just even take it over that. So my r, the absolute value of r, the absolute value of 6.28 over 6 is what? Greater than 1. If it's greater than 1, look it up, greater than or equal to 1. If it's greater than or equal to 1, diverges. Okay. All right, so what does that mean? What does divergence mean? When I plug in a 1, or well, technically here I'd plug in a 0. When I plug in a 0, when I plug in a 1, when I plug in a 2, when I plug in a 3, and I add those answers together, it's going to get bigger and bigger and bigger. Okay. Or I guess in some cases it could get smaller and smaller and smaller, but it is not going towards one number. Okay, so this diverges is saying as I find numbers and I add them together, it is not approaching any number. Okay. All right, let's try, okay, so where are we? Okay, that's that guy. So I wrote geometric, I wrote what I used or what I identified it as, I guess you can say, and then it diverges. All right, let's take a look at this guy. We're just going to keep going through examples. How are we doing on time? Okay, let's do a few more. Let's see how many we can get through here. N equals 0 to infinity, and then I've got 1 over the square root of 2 to the n power. Now, 1 is kind of nice because 1 to any power is still going to be 1. So I can actually kind of change this. Because it's a 1 up there, I get lucky. I get to do it like this. N equals 0. Notice I'm starting at 0. I can do 1 over the square root of 2 to the n power. And that's the only reason I can do that is because it is a 1. Okay, and this is geometric. Okay. Now remember, eventually it's going to be different even in this lesson, but you kind of have to get in your head what geometric looks like because we're going to see this throughout the whole chapter. Okay. All right, so what's my number in front? My number in front, if I need it, my number in front is a 1. Okay, so A is a 1, A is a 1, and R is 1 over the square root of 2. Okay, so what is 1 divided by the square root of 2? That is approximately 0.707. Okay, so it's geometric. Let's double check. I've got an n here, but I'm starting at 0, so I'm in good shape. Okay, what else? Okay, so my r, if my absolute value of r is less than 1, it converges. Okay, so it definitely converges, and that's because this is 0.707, so it is in fact less than 1. Okay. All right, and then what does it converge to? A over 1 minus r. Okay, believe it or not, this gets a little messy. Even though my a is 1, that seems like it would be easy, right? 1 over, but then it's 1 minus 1 over the square root of 2. That answer is not bad. I mean, that answer is what it converges to. We can just simplify it, okay? I don't care if you answer this on a test, that's fine with me. Otherwise, let's go through it though. Let's simplify it really quick. So this is 1, so I'm going to do square root of 2 over square root of 2, or square root of 2 over square root of 2 minus 1 over square root of 2. Okay, so I still have this 1 on top. And then it looks like I just made a big mess, right? This is 1, so I got a common denominator. So I've got the square root of 2 minus 1 over the square root of 2. Okay, so now instead of dividing, I'm going to multiply by the reciprocal. So 1 times square root of 2 over square root of 2 minus 1. And even that's not too bad, times 1, so I don't really need that. So it would be this guy. We don't really like square roots in the bottom, though so this answer is okay. This answer is a lot better. Okay, and then the last thing I could do, this is all just simplifying, so don't panic, is I could multiply by the conjugate. Notice it's plus. I could multiply by the conjugate. All right, so this gives me square root of 2 times square root of 2 gives me regular 2. Square root of 2 times 1 gives me square root of 2. But what happens on the bottom? Square root of 2 times square root of 2 gives me 2. Can you guys still see it? Barely, okay. This gives me square root of 2. But inner gives me negative square root of 2. Okay. And then last, how are we doing? Last gives me negative 1. So these cancel out because 1 was plus and 1 was minus. But I've got 2 minus 1, which is really just 1. So the best answer is 2 plus the square root of 2, technically over 1, but I don't need to write that. Okay, but all of these three are the same, and all of those three are what it converges to. Let's think about what these three mean. If I plug in a 0, if I plug in a 1, if I plug in a 2, and add them together, the sum from 0 to infinity is going to approach 2 plus the square root of 2. Okay, or this guy here, these three are the same thing. Okay, but that's kind of crazy. That in itself is, this simplifying this may be crazy, but to know that I could add all these together and it approaches 2 plus the square root of 2. Crazy stuff. Okay. All right, let's try now. This is different. Let's take a look at this. Let's talk about why it is different. N equals 1 to infinity. Okay, and I've got n times n plus 2 and then I've got n plus 3 squared. Okay, how do I know it's not geometric? Geometric, n has to be an exponent. Your n has to be an exponent. In order to be geometric, n has to be an exponent. So we do not have an exponent here. So this is not geometric, has nothing to do with geometric. Okay, so our other option is harmonic, but that's 1 over n. That comes up very, you know, it doesn't come up very, well, it comes up a lot, but it has to be pretty basic. It's going to come up if we maybe split something up, something like that. But so our other option is harmonic. Keep that on the back burner, because notice at least n is not an exponent for harmonic. And then the only other thing we have, right now at least, is the test for divergence. And so I think that's the one we're going to use. The test for divergence says, even though we're doing a sum, the test, so let's write that, test for divergence. And that's part of the, that's definitely the hard part, is to know what am I going to even use to look if it converges or diverges. That's the hard part. Okay, so test for divergence. So you have to kind of go through your file of facts, right, and pick out what rule do I have and what rule is going to work for the problem. That alone is hard, and then we still have to apply the test. Okay. All right, so the test for divergence says I'm actually just going to look at the rule. As n approaches infinity, I'm actually just going to look at this. So I'm kind of going to turn it into a problem from 8.1. Okay. And I think the best way to do this is just to multiply it out. So this is going to give me n squared plus 2n. Okay, and this I'm going to write out twice and FOIL. Okay, I'm going to get n squared, and then I'm going to do outer and inner together to save some time. So this is going to be 3n, and this is going to be 3n, so that gives me 6n, and then last gives me 9. Okay, the limit as n approaches infinity. Remember, even though I'm doing the summation, the test for divergence says I can just look at the rule. Okay, so now this turns into a problem from 8.1. Okay, how do I do this? I either do L'Hopital's rule, or I divide everything by n squared. Okay, so maybe this one, should we do, let's do L'Hopital's rule. So L'Hopital, okay, so I'm going to do the limit as n approaches infinity. Let's make sure, should I use L'Hopital's? If I plug in, you know, a big number, this is headed towards infinity. If I plug in a big number, this is headed towards infinity. So remember, it has to be infinity over infinity, or in the rare case, 0 over 0, in order to use this, guys. But I think this is the case. So we take the derivative of the top, and then we take the derivative of the bottom. 2n, let's see, how are we doing here? Plus 6, and then that guy goes away. Same thing though, right? If I plug in an infinity, I'm going to get, or if I plug in a big number, I'm going to get infinity. If I plug in a big number, I'm going to get infinity. So I do L'Hopital's rule again. Take the derivative, that goes to 2, that goes to 0. Take the derivative, this goes to 2, that goes to 0. And so my limit then, I no longer have an n, so the limit is 1. Okay, now what is test for divergence though? Because remember, we're really doing this for the sum. Let me see if I can find that. Okay, if that limit does not equal 0, it automatically diverges. If the limit of the sequence does not equal 0, my whole summation, my original problem, diverges. Okay. So my sum, if it doesn't equal 0, it diverges. Okay, if it does equal 0, it tells us absolutely nothing. Right? Okay. All right, let's stop there, and then we've got, so part B will just be 7 more examples. But like I said, the smaller, so the second one will be a lot shorter, but let's let's stop there. I think it'll just help. Or should we keep going? We're going to stop there and then just stop and click on part B. It just helps for downloading.